In this video, we're going to look at digitization in communication. That is the conversion of analog to digital signals. So we're going to focus on digitization graphs in communication. And by so doing, we are going to be using the March 2018 paper 42, question number 6. Without much further ado, let's get started. Now the question reads that the digital transmission of speech may be represented using the block diagram of figure 6.1. So we do have the mic over here, and then from analog to digital converter ADC, and then transmitted, then we're going to get a digital to analog converter, so that's back again to analog, and then there's a loudspeaker on the other side. Part of the signal at point P, that is here, on at point P on figure 6.1 is shown in figure 6.2. So this is figure 6.2. Right, so before we look at the question, let me just interpret this graph. Now this means that the signal was being sampled at 0.25 millisecond intervals. So every 0.25 milliseconds, we're going to sample it and then we digitize it. That is the conversion of this figure here that we get over here into digital. Then after, again, another 0.25 milliseconds, we sample it and then we get that. And then another was 0.25 until the whole thing has been exhausted. Now the problem with sampling at large intervals, that is 0.25, is the digital signal that you're going to get is not going to be as a good representation of the original analog signal. So in order to get a digital signal that is more or less or close to the original analog signal, we need to increase the sampling times. So the sampling rate has to be increased in order for us to do that. Right, so let's read the question. The analog to digital converter ADC samples the signal at time intervals of 0.25 milliseconds. Each sample is converted into a 4-bit number with the smallest bit representing 1 millivolt. Use figure 6.2 to determine the 4-bit number produced by the ADC at time 0.25 milliseconds. So at 0.25 milliseconds, we are going to go up. Let me change this. So we are going to go up, and then we're going to go there. Right? So we need to know the scale on the y-axis. So this is 4, this is 6. So in between 4 and 6, that's where we get our 5. Okay, so 1, 2, 3, 4, 5. So 1, 2, 4, 1, 2. So that will be 5 over there. Okay. Right, yes, that will be 5, exactly 5 millivolts. Right, then we need to convert this 5 millivolts into a digital number. There are two ways to do that. One of the ways is to use the long division method, where you are going to say 2 into 5, that is 2 times, remainder 1. Then 2 into 2, that's 1, remainder 0. Then 2 into 1, 0, remainder 1. We take our number going upwards. It's going to be 1, 0, 1. But now since they've said that they want it as a 4-bit system or 4-bit number, we're going to get it as 0, 1, 0, 1. So which you're going to write there 0, 1, 0, 1. The other way to do this is to have We know 2 to the power 0, 2 to the power 1, 2 to the power of 2. Right, so we're going to say this is 4 plus 1. Yes, so it's going to give you 2 to the power of 0, like this. So 1, 0, 1. So 2 to the power of 0 is 1. 1 times 1, that's 1. Plus 2 to the power of 1, that is 2 times 0, that's 0. Then 2 to the power of 2, that's 4. 4 times 1, 1. So 101. So proven. Okay. Then the other time where we need to sample is at 1.25. So 1.25 is right there. We're going to go up, and then we're going to go there. Remember, we take the whole number where we have gone. So this is 8. 9 will be somewhere there, and then 10 is there. So which means we take the nearest whole number, which is going to be 5. Which is going to be 8. Then we're going to convert that 8 into the binary. So that's going to be 4, remainder 0. 2 into 4, that is 2, remainder 0. 2 into 2, 1, remainder 0. 2 into 1, 0, remainder 1. We take our number going upwards, so it's going 0, 0, 0. It's already a 4-bit number, so we can write it as it is. Okay. So again, we can prove it by saying 2 to the power of 0, 2 to the power of 1, 2 to the power of 2, 2 to the power of 3, to the power of like that. Then we see. Okay, moving on. The digital number is transmitted and then converted to an analog form by the digital to analog converter. Use data from figure 6.2 to draw on the axis of 6.3 the output level of the DAC for time t is equal to 0, t is equal to t is equal to 1.5 milliseconds. Assume that there is no time delay of the transmission of the signal between point P and the output of the digital to analog converter. Right? So we've been given that. So we're going to find the values. So we've done 2. Starting from here, we've got 0. Then from there, we had 5. Then the next one, so it's all at 0.25 millivolt or millisecond intervals. Then this is going to be 10. And then this one is going to be 12. That one is going to be that, which is going to be 15. Then we've got that, which is 8. We've done it already. And then we've got the last one, which is 5 again, because we haven't reached 6. So that's going to be 5. So what do we have? We have 0, 5. The next one is 10. Then we have 12. Then we have 15. And then we have 8. And then lastly, we have 5. So 0, 5, 10, 12. So let's see. 0, 5, 10, 12. Right? Then the next one is 15. And the next one would be 8. And the last one is 5. It's right there. So we're going to go. So that's how it goes. Okay, right. So that's how you then apply the DAC, digital to analog, to get the final. As you can see, this shape does not resemble that much the shape of the original one, because there's a 4 right there, which because of our sampling rate we could not capture that. So that's the disadvantage of having this sampling rate. Right, so I hope this video has helped, and please don't forget to subscribe to the Physics Tips for Cambridge Students YouTube channel. Don't forget to like and share, as well as comment. So commenting is very important as well. Signing out.